Hello, welcome to all for this course, Basics of Solid State Devices. This course is especially for EEE students. They will learn about the basics of solid state devices. In this paper, they are they will learn the fundamentals of physics, solid state physics, and also learn about the semiconductors, energy band, and the difference between the conductors, insulators, and semiconductor also. For this chapter, they will learn the fundamentals concept and fundamental of physics about the semiconductors. See, let me introduce about the semiconductor. What are semiconductors? The semiconductors are materials which have a conductivity between conductors and insulator. Certain substance like germanium, silicon, carbon, etc. are neither a good conductor like copper nor insulator like glass. In other words, the resistivity of these materials lies in between conductors and insulator. Such a substance is called semiconductors. Semiconductors have some useful properties and are being extensively used in this means electronic circuits like a transistor, diode, and also a semiconductor devices. A transistor are also one of the family of semiconductor devices, and many of the devices are there: integrated chips, ICs, diodes, and some of the devices also there. Here we are using for germanium and silicon, the pure element is a semiconductor device. Generally, we are taking for silicon and germanium is a semiconductor material. It is a pure element material. So for this material, silicon electronic structures is 1s2, 2s2, 2p6, 3s2, 3p2. We already learned about in the higher standard level. Silicon having a 14 electrons. These 14 electrons are occupying the electronic shell. That means 1s2, 2s2. It's having, what is that? See here, what is that? It is a 1s2 and 3s2. Then what is 2p6 also there, and 3s2 and 3p2 also. See, in the silicon atom, in the outermost orbit, there are 4 valence electrons are there. 4 valence electrons there. The electron present in the outermost orbit are called as a valence electron. These valence, their behavior decide the electrical characteristics of the material. For silicon, 2 electrons are present in the 3s orbital and 2 electrons are in the 3p orbitals. Let us consider in n silicon atoms which are far apart from each other, so that the interaction between them is negligible. So in this 2 electron, that is a 2n electron occupy the 3s level and 2 electron in 3p level. See here, when the atoms are brought to closer, the interatomic, that means the interaction between increases and they now form the electronic system. The silicon atom. In this silicon atom, 14 atomic number, therefore having a 14 proton and 14 electrons also there. 2 electrons are in the first orbit, 8 electrons in the second orbit, and 4 electrons in the third orbit. It is clear that the silicon atom have 4 valence electrons. That is, it is a tetravalent element. It shows that the diagram shows that the various silicon atoms are held through the covalent bond. So this is the silicon crystalline structure. This is a silicon crystalline structure. The electronic system should obey the Pauli exclusion principle, which states that a number of electrons are in the system can have the same amount of energy. To obey this 3s and 3p level, split into multiple levels so that the electron can occupy a distinct energy level. When interatomic distance is further reduced, the 2n s level and 6n p level combine into a single bond. At a lattice spacing, the single bond is split into two bands with upper band and lower band. It containing a 4n in the upper band and 4n levels in the lower band. Generally, at 0 Kelvin, electron possess the lowest energy. They fill up the valence band fully and the conduction band remaining empty. In energy band theory, there are the three bands are there, the important energy bands are there. Number one is the valence band, conduction band, and forbidden band. With the valence band, the range of energies possessed by the valence electron is known as the valence band. In conduction band, in certain material, example metals, the valence electrons are loosely attached to the nucleus. Even at ordinary temperature, some of the valence electron may get detached to become a free electron. In fact, it is these free electrons which are responsible for the conduction of current in a conductor. So for this reason, they are called as conduction of electron. And another one is forbidden band. The separation between the conduction band and valence band on the energy level diagram is known as the forbidden energy band gap. First, we are going to learn about the valence band. The band, I already told you, the range of energy that is band possessed by the valence electron is known as the valence band. In this valence band, the electrons in the outermost orbit of an atom are known as a valence electron. In a normal atom, valence band has the electrons of higher energies. The valence band may be a complete or partially filled. In case of inert gases, the valence band is full, whereas for other material, it is only partially filled. Partially filled band can accommodate more electron. That means the band energy levels are also very close to the nucleus, and it cannot move freely when external field is applied. These electrons are called bounded electrons. See, this type of electron, the electron in the valence band expulses a strong force of attraction from the nucleus. and it cannot move freely when the external electric field is applied. This is called as a valence band. Next one is the conduction band. All metals are conducting materials. The valence electron are loosely attached to the nucleus. Even at ordinary temperature, some of the valence electron may get detached to become a free electron. In fact, it is these free electrons which are responsible for the conduction of current in a conductor. For this reason, they are called conduction electron. In this conduction band of energy levels, which are far away from the nucleus, the conduction band is the band of orbitals that are high in energy and are generally empty. Valence band is fully occupied and conduction band is fully empty. An electron in the conduction band has a weak influence of the nucleus and hence it can move freely under the effect of applied electric field and thus it produces current. It is called as a free electron. In the energy band diagram, the ranges of energy that is band possessed by the conduction band electrons is known as a conduction band. All electrons in the conduction band are free electrons. If a substance has an empty conduction band, it means current conduction is not possible in the substance. Generally, insulators have empty conduction band. On the other hand, it is partially filled for conductors. The Fermi gap is generally referred to the energy differences between the top of the valence band and the bottom of the conduction band. Band in insulator and semiconductor. The types of material. The materials can be divided into three types based on the values of energy gap: insulator, conductor, and semiconductor. See the energy level diagram. In this energy level diagram, insulator have wide energy band gap. Example of insulator: wood, glass. Insulators are those substances which do not allow the passage of electric current through them. In terms of energy band, the valence band is full while the conduction band is empty. Further, the energy gap between the valence band and conduction band is very large, approximately 15 electron volt. Therefore, a very high electric field is required to push the valence electron to the conduction band for insulator. For this reason, the electrical conductivity of such a material is extremely small and may be regarded as nil under ordinary conditions. At room temperature, the valence electron of the insulator do not have enough energy to cross over to the conduction band. However, when the temperature is raised, some of the valence electron may acquire enough energy to cross over the conduction band. Hence, the resistance of an insulator decreases with the increase in temperature. That is, an insulator has a negative temperature coefficient of resistance. And second diagram for conductors. Conductors generally all metals. Example, copper, aluminum are those substances which easily allow the passage of electric current through them.